Module 5, we're talking about modeling electrical circuits and essentially coming up with either a transfer function or an ordinary differential equation. And so one of the things we know is that if we have a transfer function, we can actually convert that to an ODE and vice versa. So I'm taking a little bit different approach than what you see in one of the Professor Miller videos. It's an optional video, so maybe you're not going to watch it, but I do encourage you to, because it's a different approach. In Professor Miller's approach, he pretty much keeps in the time domain and writes differential equations without taking the Laplace transform of individual circuit elements. All right, the approach I wanted to do is to show you that you can actually take the Laplace transform of circuit elements, and the nice thing about that is that the Laplace transform turns everything into something that acts like a resistor. Okay, we call that an impedance if it's something that is acting like a resistor. Okay, so let's get started. Let's say we had a resistor, and one of the things we know about a resistor is that Ohm's law applies, and that V is equal to I times R. Okay, and so if I took the Laplace transform of both sides, I would get V is equal to capital I times R. All right, it's where lowercase v is the time domain, uppercase v is the Laplace domain. Same thing for I. Lowercase I is time domain, uppercase I is Laplace domain. So I took the Laplace transform of all the signals here, and you notice this still looks like Ohm's law in the Laplace domain. Its voltage is equal to a current times an impedance, and this time the impedance is R. Okay, so let's switch that over. Let's do the capacitor. And one thing we know from physics and from your circuits class is that I is equal to C dV dt. Okay, so I can take the Laplace transform of both sides, and when I do that, I get capital I. Let me move this down. A little more room. Okay, and I get capital I is equal to C S V. All right, the S comes from the fact that this is a derivative. Okay, so I can rearrange this. I can move the V to one side, and what I would get is that V is equal to 1 over CS times I. All right, so I want you to put on a pattern recognizer here. If you were looking to make this fit the form of Ohm's law, then this part would be playing the role of the resistance. Okay, so we call that an impedance, and ZC is 1 over CS. And from there, you can work all the circuits that have a capacitor as if Ohm's law applies, because it's fitting the form of Ohm's law, where V is equal to some constant or some mathematical expression. In this case, it's a function of S times I. Okay, so we treat a capacitor as 1 over CS. All right, and we can do the same thing with an inductor. Okay, and so what we have is that V is equal to L di dt for an inductor. Take the Laplace transform of both sides. You get V is equal to L S times cap I. And in this case, the impedance of the inductor would be L times S. All right. So if I had a simple circuit, okay, all right, I have a circuit here, plus minus VI of t, and here's a resistor, here's an inductor, and here's a capacitor. R, L, and C. I can move this circuit into the Laplace domain by taking the Laplace transform of everything. Okay, so the Laplace transform of VI would be capital VI of S. The transform of a resistor R, resistors stay resistors in the Laplace domain. Okay, and then the inductor becomes LS, and the capacitor becomes 1 over CS. Okay, so that's what the circuit looks like. And now you can do circuit analysis just like you did before with purely resistors. Okay, so that's where we'll pick it up on the next video.